just go through these initial functions and talk about them. And I know these are kind of small, so I will be drawing them on the board as we go through. And these are functions I think that you've seen before, and we're going to be putting them together in several different ways. So kind of the most elementary function that we have is just a constant function, where on an xy graph we have something like x equals 2. And you say, well, not x equals 2, y equals 2. And you think, is that a function really? Well, it is, because for any value of x, the value of y is 2. And so it looks like a straight horizontal line, like this. And so there's not a whole lot that goes on with this, obviously, because it's just a constant. But it's a really good thing to think about, that this is, in fact, a legitimate function, and a function that we can test certain ideas against. The next one is the most basic linear function. So we have x equals y, or let me write it more in a functional order, y equals x. And this is just a straight line that goes through the origin. And if you like measuring things in degrees, this is a 45-degree angle, and it just basically equates x and y. So every line that has an equation, y equals mx plus b, we can make by some sort of alteration of this really basic line here. Now, the third one is absolute value, and this is one that I want you to keep in mind, that when we have certain things that we're looking for, like when we talk about differentiability or continuity or any of these ideas that we're going to get into, a good thing to test your ideas against is the absolute value function. And so the absolute value, if you recall, just gives you the positive version of the size of a particular number. So when x is positive, it just equals y. Now when x is negative, it equals, the function is, okay, then the function makes x negative, and so if you have, for instance, negative 3, then negative 3 is positive 3, so y then equals 3. And so we have that point there. And it comes to a nice sharp point here, where as x decreases down to 0, x remains unchanged, but as soon as we're non-zero and negative, then we get the positive version of that negative number. So it's a very sharp corner there, and things really change. And so this is one of those functions that may seem kind of simple or so, but I guarantee you, if you think about, if I'm going to ask you questions about, do all functions do this or do all functions not do that, this is the one to think about, that you can test those ideas against. Now we have some other functions. We have the function where, and I'll use the functional notation, f at x equals x squared. And so this is the basic parabola. You have kind of the same thing going on that you have with the absolute value, where the output values are always positive, whether x is positive or negative, but we have this nice curve, and it doesn't come to a sharp point, it comes to a vertex, but it gradually goes to the vertex and gradually moves away from the vertex. Now, we're going to contrast that a lot with x cubed. And so the characteristic about x cubed is when you cube something, it retains its sign. And so if we take 2 cubed, we get 8. 2 times 2 times 2 is 8. If you have negative 2 cubed, we have negative 2 times negative 2 is positive 4 times negative 2 is negative 8. So we have, instead of returning up to positive values, when we have negative x's, we get negative y's as well, or f at x takes on a negative value. Now, these 5 so far, we can put in any value of x, and we get a value of y. Okay, so we talk about the domain as what's all the possible inputs of these. Is this is going to drive me crazy. Okay, so the domains of these things are all the values of x, positive and negative. Now here's one where we have a restriction on the domain, and this would be where f at x equals the square root of x. Okay, and this one will look like this, where it comes down to, you can take the square root of 0 and get 0, but you can't take the square root of a negative number and get a real number out of it. Certainly you take the square root of -1, you get I, the imaginary unit, but we're not going to talk about imaginary numbers at all. We're only concerned about real numbers, and so there's, negative values of x are not part of the domain. And so this is going to be a nice one to test some ideas against as well. Okay, and then we have 3 more. Kind of the, if this one is associated with x squared, it kind of undoes that in a sense. We have the cube root of x as well, and I'll write this one on over here. Now you can take the cube root of a negative number, right? If you take the cube root of 8, you get -2. So here's one where all negative values and all positive values and 0 work for the cube root, and we'll notate that with a little 3 as the index on the root here, and so we have the cube root. Now there's going to be 2 others that we'll talk about. One is the reciprocal, and the other one is the reciprocal squared. So if we just take the reciprocal as 1 over x, and so 1 over 1 is 1, so we have this value that's sitting here, but as we take larger numbers, the reciprocal becomes a smaller number, like 1 over 100 is 1/100th, and then the same thing happens when we have small numbers, like if we take the reciprocal of 1/100th, we'll get 100, and so we get this curve. With the reciprocal, it retains the sign, and so we have this this curve that has negative values that stay negative. When x is negative, y stays negative. And then we're going to have a variation of that one, which will be the reciprocal of the square. Now what happens here is that we have, even though the values are different, the appearance of the graph looks about the same on the positive side, but on the negative side, since we're squaring x, it's going to give us the positive value. So for instance, if I take -2, if I take the reciprocal of -2 squared, what I get is 1/4, and so I'm going to have something that looks similar to this graph, except that the left-hand portion of it is going to be above the x-axis. So those functions, we have 6 here and 3 there, so there's 9 functions. I'm going to refer to these collectively as the toolkit functions. And so, like I said earlier, it's not a universal thing. You can't go up to a mathematician and say, you know, what are the toolkit functions, and they'll tell you these 9 functions. But our textbook calls them this because we're going to be using this as the basis for our discussion of all the functions from here on out. So certainly not every... Let me see what's going on. Okay, so we're going to use this as the basis for building other functions and try and understand functions in general by using these. So I would suggest that you memorize these just as you know, essentially that, a toolkit, just a variety of functions that we can think, okay, do all functions do this? And if you think about the toolkit functions, you'll generally get an answer, well, yes, all functions will do this, or no, all functions don't do that. You can usually find an example to either prove or disprove some of the theorems and conjectures and things of that sort that we're going to make. Okay, so let's talk about domain and range. And I don't think I have all of them listed up here, but we'll go through and look at domain and range. Remember what the 2 words mean. The domain is all the possible input values to a function. The range is the set of all possible output functions. And so if we look at the first one, we can put in any value of x that we want. So if we say f at x equals 2, is what we're saying here, x can be any value, the output value is always 2. So our domain is all real numbers, the range is just plain old 2, or whatever constant that we declare there. So for the second one then, when we look at just f at x equals x, here the domain and the range are both the set of real numbers, right? We can put in any real number and we can get out any real number. So if you say, well, let's try any big negative number or any number, we get the same number on the input and the output. And it's going to be true that we'll find that for any linear function, anything that we can express as y equals mx plus b, we're going to have the domain as all real numbers. The range is going to be all real numbers as well. Now, x squared changes a little bit. We'll go over here. X squared, when we have, we can put in any number, but we only get 0 or more as the range. And so here's one that has a restriction, not a restriction, but a limitation of its range where you can't get a -2 out of this function. There's no value of x that makes f at x equals -2, right? So all the input values can be any real number. The output values are only non-negative real numbers that make 0 and all the positive numbers. If we look at the reciprocal now, where do we have the reciprocal? Over there. We're looking at the domain as being anything except 0. So I'm notating that with two intervals. One is -infinity to 0, and I'm going to have the union of that with 0 to infinity. And so there's a gap there because 0 is not included in either of those intervals. So that's the way I notate, that x cannot be 0. So we have a domain restriction that says, okay, when the denominator of that function, just x at this point, when it's 0, that's not part of the domain, and there's no corresponding value in the range that will give us 0. So if you try and solve for 1 over x equals 0, there's no value of x that will give you that. Now the same thing with the 1 over x squared, except if you look at what the range is, we still don't have the possibility of getting a 0 out of the function, but we only get all the positive numbers. So the domain is the same as it is for 1 over x, but the range is just 0 to infinity. So we'll move on over to the square root, and now the square root is the first one where we have a domain restriction, and it has to be 0 or more. That we can't have any negative number because then it doesn't compute to a real number. The range, of course, then is all non-negative numbers. We can get a 0 out of it. We can get any positive number. Okay, so let's look at the absolute value now. The absolute value, the domain and the range of this look exactly like we have with x squared. So we can put in any number, we get any non-negative number out as the range, and the cube then, of course, the domain is going to be all real numbers and the range is all real numbers as well. And I think I hit all of them. Perhaps the cube root of x is not explicitly there, but what that is, of course, is the domain and range are both all real numbers. Okay, so what we want to do is think of this both graphically and analytically, what this function is. And so we're going to answer the question, what's the domain of this function? So if you look at what's going on here, we have a 2 times something and we have an x plus 4, but what really is happening with this function is that kind of the square root is like the main action, so to speak. That's the thing that if we're just adding a number, then we get a linear function, so there's nothing that comes out of it in terms of restrictions of the domain or limitations on the range. But we know we have a limitation on the square root where we can't take the square root of a negative number. So if we're trying to look for the domain of this thing, what we do is we solve for x plus 4 equals 0, right? Because if we look at this, we know that x can't be 0, or x can't be less than 0, So what we want then, if we have something else in that square root, in this case x plus 4, we want the x plus 4 to be greater than or equal to 0. And if we solve for that, then we get x has to be greater than or equal to negative 4. So there's our domain. It's the set of numbers that are greater than or equal to 4. So we just set that up to what it has to be, and there's our interval. So let's take another one. If we say g at x equals 3 over 6 minus 3x, this will stop eventually. We're looking at the denominator. If we look at our toolkit function there, where it's 1 over x, and we know that we have a domain restriction where x can't be 0. In this case, instead of just having a plain old x, we have a 6 minus 3x. So we know that that can't equal 0, because then we have division by 0. So what we'll do is we'll say the first line here says that it can't be 0. So what I'm going to do when I'm setting it equal to 0 here is I'm looking for what are the values of x that make it 0, and then that's what I'm going to exclude. Okay, so there's the reason for me flipping from a not equal sign to an equal sign. Here I'm saying that this doesn't work in my function, so when is x 0? And so I just solve for x, and I figure, okay, when x is 2, then I have to exclude that from my domain, and so I can write it as an interval now, as negative infinity to 2, and then with a union of 2 to infinity. All right, so that essentially says we have a domain restriction there at that x cannot equal 2. Okay, so now what I want you to do is you find the domain of this function. Okay, so a little more complicated. It has both elements in it, both a square root and a reciprocal. So see what you can do to figure out what that domain is. And in fact, I have a cash prize here. Any of you Romanian? Anybody Romanian? Anybody been to Romania? I haven't either, but I was cleaning out my closet the other day, and I found a Romanian 1,000, what do they call them? Lei, L-E-I, note here. And I'll give this as my first cash prize for getting the correct domain. So there's an incentive for you. Raise your hand when you got it. You'll get the, yes?
I think I have, I'm not sure though. Okay, so x can't be equal to negative 3 for the denominator. And then for the numerator, I think it's x has to be greater than or equal to 2.
Okay, so let me test that. If x is greater than 2, then 10 should work, right? So if I put 2 minus 10, I get negative 8. So that doesn't work.
Okay,
so
x has to be less than
you got it wrong. We'll ask somebody else now. Sorry, you missed your 1,000 lei or whatever it is. Yes? It's less than or equal to negative 2. Not negative 2, really? So if I put in a 0, am I okay? Because 0 is not less than or equal to 2. Okay, Jolene. Yeah, less than or equal to 2. So here you go. Here's your cash prize. It's not negative 2. I'll show you how we calculate that. Now don't spend that all in one place, okay? If you look on the internet, you'll find that Romania has changed its currency. It now has LEU instead of LEI, however you pronounce that. And an LEI, which is what you have, that 1,000, we'll call it a lei bill, is worth 2.5 cents. Okay? Yeah, well, anyway, it's still money, right? Okay, so the way we do this is you say, what can't it be? So what we have to say now is that 2 minus x has to be greater than or equal to 0. And so there's your key equation, because you're just saying, okay, what's inside the square root has to be greater than or equal to 0. So now we solve it. We're going to add x to both sides. And so we get this, or to write it a little bit more conventionally, we have that. All right, so it's just a matter of setting up the equation where you know what has to happen. This expression, whatever it is, has to be greater than or equal to 0, and then solve for x, and then you have the correct expression. Now the other one, the x plus 3, that's a little easier. You can spot that right away, that if you get x equals negative 3, we have division by 0, which can't happen. So how do we express this now in intervals? If we look at x is greater than 2, or equal to 2, we're going to say this. But if x can't be negative 3, all right? No, I think we're the other way around. It has to be less than. I'm writing it backwards. Let me make some space to do this properly here. So we're saying x has to be less than or equal to 2. X cannot be negative 3. And so what we have is this expression here, or this interval, for the first one, and the second one. Now, negative 3 is in this interval, so we have to do an exclusion there. So what we're going to do is make this interval go up to negative 3, and then we're going to not be at negative 3 with the parentheses, and then we're going to start again at negative 3 but not include negative 3, and this can go up to 2. And so here's your interval expression that basically tells you that x has to be less than or equal to 2 but not negative 3. Okay, everybody follow? Feeling rich, Jolene? Yep. Okay, so here's the process. All right, and then to write it as the interval, to make the notes complete, there we are. Okay, so here's my maddeningly small writing. We're going to talk about piecewise functions. Now, piecewise functions are functions that are defined by certain pieces of their domain. Okay, so the value or the formula that we're going to use for the function depends on its input value. All right, now you always, not always, but oftentimes people look at piecewise function and they get really confused, and it's really, kind of a roll your eye over in this again. But you've used piecewise functions longer than you perhaps realize. So the example that I like to use to demonstrate this is going to the movies. Okay, so let me say first how to notate these things. So we're going to say f at x equals, and then not just one expression. We're going to use that. We're going to use this framework where we have that brace that we use to notate a set. Okay, so we'll have and actually look at this function as a set. So we're going to have a first formula if x is in one domain part, and then a second formula if x is in another part of the domain, and a third formula if x is in the third part of the domain. Okay, so let's go first, look at movie tickets. And if you go up to a window and buy a movie ticket, you often see something like this, okay, where depending on your age, you'll pay a different price. Okay, so if you're under 14, you pay $7. If you're between 14 and 64, you pay $15, and if you're 65 over, you pay $10. Now notice the boundaries of those things are pretty well defined. Gosh, this has, I can't believe this is happening this frequently. Okay, so notice the boundaries. You have under 14 and 14 and above. You don't go up to the window and say, oh, I'm 14, and then they say, well, it's $7 and $15. That doesn't work. It has to be exactly one value, right? I mean, you kind of look at the guy in the booth, kind of funny if he gave you two prices for one age. Similarly, it's at 64 or 65, when you're 64, it's one price. When you're 65, it's the other. It's not between 14 and 65, it's 15, and 65 and over, it's 10, that would mean that 65 has two values. So this is truly a function. For any age you give it, you have a price. Okay, so one-to-one correspondence, or not one-to-one correspondence, but you do have this function where you have exactly one price for any age that you have. Okay, so let me notate this then using the format that I put earlier in the chart. So I'm going to define my variables, really important. So A is age, P at A is the admission price at age A, and so I'm going to write this function that P at A is this set. So 7 if A is less than 14, 15 if 14, if A is between 14 and 64, and if you're over 64, it'll be $10. So this is very simple. I have three constant functions here. Remember, a constant function is that for whatever value of x you have the same number. So I'm defining a part of a domain. The part of the domain that I'm defining is when a is less than 14, my function is a constant, it's 7. So when I'm between 14 and 64, my function is still a constant, but now the constant is a different value. It's going to be 15. And if you're over 65, then you have another constant, and this is 10. Yes?
For the last one, could you also say if A was greater than or equal to 65?
Yes, yes. And yeah, so long as there's no overlap. So, that the two are the same. And actually, it's probably better because we're talking about ages as being integers. If you say, well, what's 64 and a half? On my chart, it's not, 64 and a half is greater than 64, so, you would be paying the 65 price. So probably some, if you're worried about fractions, then you have to be, worried about, how that is a more precise definition than what I put up. Okay, so let's make a graph of this. Now, to make a graph of this, what you do is you just look at the domain part that we're interested in and just draw the graph normally. So, what I have here is from 14 and below, my function is my toolkit function of just a constant at 7. And notice I'm saying that this is less than 14, so I'm not including 14. Here, I'm at from 15 to 64, and I'm including the endpoints. And here, I'm not including 64, but anything over that. So perhaps this needs to be corrected a little bit because 64 and a half would be in the higher price range. But hopefully you'll get the gist of this, that we basically just look at a limited domain and just graph that one piece of it, then go on to the next part of the domain. Okay, so here's a function now. I'd like you to think about this. My function is going to be, and I'll write this on the board. So my function is going to be x squared. If x is less than or equal to 1, it's going to be 3 if x is between 1 and 2. And notice where my equals and inequality signs are, and x if x is greater than 2. Okay, so let's test some values. F at -1 is what? Anybody know?
X squared.
It would be what?
X squared.
X squared. So what is -1 squared? It's going to be 1, right? And how about then f at 1.5? It's going to be 3, right? It's a constant at that point. F at 2? It's still 3, right? Because we're in that part where it's x is less than or equal to 2. Since we're equal to 2, the second line applies. And the third one, f at 10 then, x is over 2, so then it's the last one, f at x then equals 10. All right, so the way we read these is kind of backwards. We start from the right and we go to the left, where we say, okay, I have a value of x. Which of those expressions in x is true? And so if I'm looking at f at 2, for instance, well, the first x is not less than 1, but x is between 1 and 2. It equals 2. And it's not greater than 2. So it's the second line that applies, so I look at the function definition, and in this case it's a constant. Okay, so we have these values like that. You think. Okay. So let's sketch this thing now. Sketch this graph and see what it looks like. So the first thing that we'll do, of course, is draw our axes. And then what I'm going to draw is x squared. And you know what x squared looks like because it's a toolkit function. But I'm going to only plot it up to 1 because my domain stops, for this section, it stops at 1. So here's my 1. And if you want to do this, you can graph the whole thing and then erase the parts that are not in the domain. And it includes 1, so I'm going to put a dot there. Now the second part, if I'm between 1 and 2, I have a constant, which is 3. So if this is 1, 2, 3, it doesn't include the 1, but it does include the 2, so I'm going to have a straight line in that part. Okay, so there's the part of the function in that segment of the domain. And then the last one is we're just, we rely on our toolkit function x equals y, which is just a straight line, but we're only going to start it at 2, and we're not going to include 2, but it goes up like that because we just have x equals y at that point. So drawing these things, I know sometimes it can be kind of confusing and things, so all you do to concentrate on this thing, I know this is very distracting here, but the thing that you do to draw these things is just to look at the part of the domain. So graph what you think the graph looks like, and then erase all of the parts that don't apply to the domain in that area. Okay, onward. Okay, so let's talk about the composition of functions. If this thing drops out again, I'm just going to go ahead and lecture from the board. You'll have the notes and the recordings only up to where this thing drops out the next time, so it doesn't get too confusing. Okay, so a composition of functions. What this means is that we're going to take the output of one function and make it the input of the other of another function. And so we're going to notate this like this, where we have f at g at x. Or we're going to talk about f composite g, which is the same thing. And we're going to notate this by putting that little circle in between the f and g. So you read that as f composite g of x. Now this doesn't mean times or anything like this. What this means is that we're first going to evaluate g and use the result of that, and then evaluate f based on that value. So one way to think of it is I have these machines, and x gets processed by g, and so we get this value g at x, and that goes into f, and so we get f at g at x. So we work from the inside out, where the inside function is done first, and then whatever value we get out of that, we apply to the outer function. So if we have two functions, let's say g at x equals x plus 2, f at x equals x squared. If I'm going to say x equals 3, I'm going to say, okay, g at 3 is 5, and then f at 5 is 25. So I'm going to say f composite g of 3 is 25. Okay, everybody follow that line of reasoning?
Can you say it one more time?
Yes. We're going to start from the inside, and so if we assign x equals 3, then we'll evaluate the inner function first, that g at x, and so since g at x equals x plus 2, if x equals 3, then we have 5. So g at x equals 5. Now f at x equals x squared, so now what we're putting inside the function is g at 3, so that makes it 5, so f at 5 is 25. So we work just like this process, you know, where we first apply g, the output of that is now the input of f. Okay, so let me start just from the board here, and we'll see what I can do here. Okay, so let's have one function that's defined as this in a table, and the output is 4, 2, 1, 3. And I'm going to have another function where I'm going to call this 3, 1, 2, 4. Okay, so what is f at 3? It would be if x is 3, f at 3 is 1. Okay, so let me explain my tables then. So for any value that I put into the function, this is what I get out. So this is the domain, this is the range of f. Okay, so if f at 3 then is x is 3, f at x is 1. So by the same kind of reasoning, if I take g at 1, what do I get? G at 1 then equals 3. Okay, so I can say then that g at f at 3 equals 3, because this simplifies into g at 1, which is 3, you see, because f at 3 equals 1. Okay, so here's one for you to try then. G at f at 2, what does that equal? Who said 1? Great, okay, that's correct, and I have no money to give you, okay? So we say f at 2 is 2, and then g at 2, okay, is 1. Okay, everybody good there? How about another one? Let's try f at g at 2. What do we get there? 4, right? We go, first we evaluate g. G at 2 is 1, and then f at 1 is 4. So we get 4. Okay, so now let's use formulas here. That's all well and good for a table. Let's say we have these are our two functions. So let's look at how we make a composite here. So let's say I want to find out what is f at g at x. Okay, so we can go through this of calculating, values. Like if I give you, okay, if x equals 3, we can go through the same process that we went through here and calculate what the value is. But since these things are algebraic, we should be able to put the two together and come up with a single function that represents the composite of both. Okay, so let's see how we do this. So remember what we do is we do the inner function first, and then we do the outer function. So the way I would recommend that you do this is use parentheses. All right, so let me, I'm going to change the color of this. This might help a little bit. If I were to write just f, the function f, and I'm going to use it as just with parentheses, I have this form, right? So forget the g at x right now. Whatever I put in, I'll even erase it. So this is a way to define f. I would put in an x here, or I could put in a 3, or I could put in anything. So if I put in a function now, let's say g at x, my g at x would come into these values here, right? Because whatever I evaluate, whatever value this is, I'd plug in there. So if I were to write this thing all as, I'm going to put g at x in here like this, I'll use the same framework of writing the parentheses, and I'll just pop the function right inside the parentheses. Okay, so now I have an algebraic expression that represents f composite g at x. I still need to simplify it, but I at least have one that's put together. So if I want to simplify this, I'll say, okay, I have to square this, so this becomes 4x squared plus 4x plus 1 minus 2x minus 1. Did I do that right? And so when I combine my terms, I get 4x squared, and then plus 2x, and that's it. So there's my function. So I can check this, if I want, by putting in some values. Let's say I want to find f composite g at 2. So let's do it the way that we did it over here. If I say g at 2 equals 2 times 2 plus 1 is 5, and so then f at 5 is going to be 25 minus 5 is 20. So this f composite g at 2 is going to be 20. So let me see what I get here. 4 times 2 squared plus 2 times 2. So this is going to be 4 times 4 is 16 plus 4, and sure enough we get 20. So we can make a composite function by substitution, and then simplify, and we'll get a single function that represents the composite there. All right, so why don't you try one? We'll say, there are my two function definitions. And what I want to do is I want to find f composite g, and I also want to find g composite f. And just for the fun of it, we'll say f composite f and g composite g. Okay, try those. Okay, so anybody get the first one yet? Yes.
1 of x plus 1.
1 over x plus 1. Good. Okay? Everybody see how that worked? So let me do it the way that I would do with parentheses. Okay, so the outer function is 1 over whatever the argument to that function is. And so that function, the inner function, is g at x, so I'm going to put in parentheses, inside my parentheses, what g at x is. And so I get that 1 over x plus 1. How about the second one?
1 over x plus 1.
Okay, we get 1 over x plus 1. And so using the framework that I have here, where I'm going to say g at x is this plus 1, then I'm going to pop f at x in here, and I get that. Okay, you see how this is working? You can, just set up the outer function, drop in the inner function. How about f at x? How about somebody else now? Okay, yes.
Is it 1 over x?
1 over 1 over x, and how does that simplify? Just x, right? So the reciprocal is just plain old x. And you're Sean, right? All right, I'm getting there, All right, and how about the last one then? G at x. Yes?
X plus 1 plus 1.
X plus 1 plus 1, which you get by saying this plus 1, and you put an x plus 1 in here, so that simplifies to x plus 2. Okay, so how are we going to use this in calculus now? This is going to be composite functions. You're going to live with pretty much from here on, because a lot of the things that we'll do that are rule-based for derivatives and integrals are going to be based on your ability to recognize composite functions. So it's all well and good to make a composite function, but what we're going to do is we're going to look at a function and we're going to make individual functions out of it. So, for example, if we have f at x equals 2 plus the square root of x minus 1. So we can make this a composite of two different functions, okay? So let's say one function, if I'm going to say g at x, I'll say is 2 plus the square root of x, and then I'm going to say h at x is going to be x minus 1, and so I can say that g composite h at x equals 2 plus the square root of x minus 1. Okay, so if I'm going to look at the format that I had before, where I'm going to have g at whatever is going to be 2 plus the square root of whatever. Okay, so I'm isolating this innermost function, this x minus 1. I'm saying, okay, everything else is going to be the outer function, and then my inner function is going to be this h, which is just x minus 1, and so we'll get our x minus 1 like that. Now the thing about this is that there's many different composite functions that we can make out of this. This is only one way. Let me say that g at x equals 2 plus x. Then h at x would have to be the square root of x minus 1. Right? Because if we take then g composite h, g is 2 plus my inner function, and the inner function is this, so when I drop that in here, I get where I started. So depending on what you want to do and what looks attractive in terms of future steps from this thing, we can look at this as a composite function of two functions in two different ways. Now we can say, okay, we can do this with three functions where we can make a composite, so we can say g at h at k at x, and then we can get kind of ridiculous about this. But realistically, you're going to be looking at it this way, where we're going to say, okay, here's a function, and we'll be able to zoom in on certain things and take a step back and look at the larger outer functions. So it takes a certain amount of practice to do this, and you'll be doing this in, like I said, for a number of different purposes, in taking derivatives, things of that sort. Okay, so here's one for you to try. I have now I can think of at least 3 different ways to do this. Okay, so come up with 2 functions whose composite gives me this overall function f. Okay, Grant, did you get something?
How about g of x equals 1 over x? And h of x equals the square root of x minus 1.
Okay, great. Anybody get anything different? Yes.
I put 1 over the square root of x, and then h of x equals g of x squared minus 1.
Okay, great. And there's perhaps a third one in there too? Anybody? How about this one? Okay, so there's 3 different ways to do this, and perhaps if we got really creative, we could figure out a few more. You really, look at these things in this fashion. Now, where this is going to be helpful is, we know what, in the toolkit function, what this does, right? We know from a toolkit function is what this one does. And so, by blending these things together, we can start to see some interactions. And we're going to have some rules that say, okay, we're going to treat reciprocals a certain way, and so we'll treat it a certain way and then multiply it by whatever the rules apply for what's inside the function. So these things are going to nest, and developing this kind of vision, looking at functions as an assembly of several functions is really, one of the going to be kind of a recurring theme for us. Okay, so we're going to talk next about translations and transformations, and this is going to be a certain kind of composite function, where what we're going to do is say, have a function we're going to put it in this form, where we have another function that comes from a constant times really one of our toolkit functions first, and then instead of just x, we're going to have x minus h in there, and we're going to add a k to it. And what this is going to do is allow us to move these functions, these toolkit functions, around, and it's also going to allow us to to either stretch or shrink them in either dimension. And so it'll take some of these. You can perhaps see quickly that the line is really going to be some sort of a constant. If we start with our function as just y equals x, it's going to be some constant times x plus this b, where the b is the intercept. Okay, so here's a very simple one that now, instead of just this line that's a 45-degree line, we can change its tilt, we can move it around and all that. And we'll be able to do that with all of our toolkit functions. And that's going to be what we do for Monday. So anyway, have a good weekend. Do something nice for your sweetheart tomorrow. Or at least call your mom, okay? Yes. Sure, okay. So,
Every single question right
okay, so we got the set of points from negative 2 to 2. So negative 2 is like this, right? Now, do they want you to include the endpoints? So we'll do it like this, okay? And then, since we want to exclude 8, we're going to use this. And then to exclude 3,
Okay, gotta get to class. I was like, I'm done with my Advil. And,
because what this will do on a number line is it's going to do 2.
if you knew you didn't have Advil, why didn't you buy
And
some?
8. Okay, what we have is this up to 3. That's this. And then 3 to 8 is like this, and it excludes that. Okay, so cut it up into pieces. That one.
And does the work like automatically?
Yes, yeah. I can. It accumulates the scores. I can see what what your prior answers are and things of that sort. So usually around exam time, what I'll do is I'll take the score to date and then put it into Moodle so you can see the impact on your grade. Tell me your name.
Dara.
Dara? Yeah, great. Okay. I'm trying to learn everybody's names now. Okay, great.
There's a lot of.
All right. What you got?
I'm just getting this now, and I was trying to log on Moodle last night, but I wasn't able to because I'm not registered for the class. So
Yeah.
There was no way I could do the homework.
Yeah.
So
Okay.
Can
You need to have Professor Hummaker sign that. He's down
the one
the
you
hall.
told me about.
Yeah.
Oh, okay.
That's the guy who puts you in the class. I don't.
Okay.
I have a quick
And
question,
how are you?
Mr.
Yeah.
Holmes. I'm good. I had a little trouble last night with the homework,
Okay.
with range. I know range is y and domain is x,
Mhm.
but the graph was like this last night and the homework problem was like this. So it went like this.
Mm-hmm.
So this here was 24, and this point here was 6. And the other one before I was able to do, because the other graph the night before, the one that was later was, it was like the here, I think this was like 2, and this was like 4. And for the range, I wrote in brackets it was 2, 4,
Mm-hmm.
and it accepted that. But then over here, when I try to do that with this one, because it's like a curve,
Because what you want to do is you want to have the minimum value, which is
Mhm.
6, but what's the maximum value?
and so
It's not 24, it's
that
right here.
one.
So
So
whatever
it
is
was
here,
30,
30. Okay, so this goes up to
and then
30.
close brackets. Why is it 30? Because of the art?
Because we're not worried about the order, we're just looking at all the possible values. And so the question to ask yourself on range is it possible to get a 30 out of this thing? Sure it is, where x is that, okay? So this has nothing to do with order. What it has to do is, what is this interval between here, the top and the bottom, okay? Where it corresponds on x is not important,
Do you think you,
from the standpoint of what the range is.
do you think you have a good weekend, Mr. Holmes?
Oh, you're bringing in all your cool toys.
Right.
The only thing a math class gets is more chalk.